So we've been talking about factoring polynomials in order to solve them, but let's think for a moment, what does factoring mean? To factor a number means to break it into smaller numbers that you could multiply together to get that original number. So when we are factoring a polynomial, we're trying to break it down into monomial or binomial factors, and then we can set each factor equal to 0 to figure out its value. Kind of like we did in Unit 3 when we took those quadratic polynomials. We factored them into two linear binomials and set each linear factor equal to 0 to solve. So now we're going to have higher degree polynomials, and it's going to become more and more challenging. Factoring is going to become more and more difficult. For example, x to the fourth plus 2x squared minus 8x minus 16. Even factoring that by grouping isn't quite going to be enough at this point. So our goal is to take out a factor and express it. For instance, we start with a cubic polynomial here, a degree 3. If we can find just one binomial factor like x plus 5 and multiply that by a quadratic, that's what gets us back to this cubic polynomial. This is something that we could easily factor once we break it down. Starting over here, x cubed plus 2x squared minus 13x plus 10, we can't really do any factoring at this stage, but if we can get it down to a more manageable degree, like a quadratic degree that we can easily factor, we will be all set. This is called a depressed polynomial right here. Doesn't mean that it's sad in any way, it's just less 1 degree, a depressed polynomial. So let's think about how we can get to that. Well, for instance, if I took the number 76 and I was trying to come up with numbers that multiply to give me 76, I know it's even. So right away I'm going to divide it by 2, and that leaves me with 38. So I know that 2 times 38 gives me 76, but maybe I want to break it down even further. Well, I know it's even, so I would say 2 times 19. And now I've broken it down as far as I can. That's our goal. Our goal is to try to find one polynomial that we can divide into this, one binomial rather, that we can divide into this polynomial, which takes us to our factor theorem. The binomial x minus a, we usually have that in parentheses, is going to be a factor of the original polynomial, f of x, if and only if f of a equals 0. So let's think about what that means. Something's going to be a factor if when you divide by it, you get 0. So if we go back to another example like 24, is 7 a factor of 24? Well, of course it's not. We know that. We know 7 is not a factor, but why is it not a factor? Because when I divide by 7, I get a remainder of 3. If you get a remainder, what you started out trying to divide by here is not a factor. But if you try to divide by, let's say, 8, this divides, we get a remainder of 0. So 8 is a factor. The same thing's going to happen here. If we divide by something and we get 0 for a remainder, it's going to be one of our factors. Now, to show that x minus 5 is a factor, we can just go back to our synthetic division. And notice that we took the opposite of 5 and put it right down here into the box. Then we took all the coefficients, 1, 2, negative 13, and 10. 1, 2, negative 13, and 10. We brought down the 1, multiplied it by negative 5, combine 2 and negative 5 to get negative 3, multiplied that by negative 5 to get 15. Combine, going downward, negative 13 and 15 gives me 2, negative 5 times 2 gives me negative 10. When I combine those, I get a remainder of 0. That means that x plus 5 is a factor of this original polynomial, because when we divide by it, we get a remainder of 0. This is great because now we started with this complicated polynomial. We found one factor and we took what's left. Remember, we get it from right here at the bottom, 1x squared minus 3x plus 2. And here we have it written right here. That is easily factored right over here. So now I can say that this cubic polynomial can be expressed as these 3 factors. So let's practice that. We're given one factor. This is one of the factors, and we're going to try to find the other 2 factors. So the first step, we want to take this polynomial and divide by this polynomial. We could use long division, but again, doing synthetic division is our friend. So 1, 1, negative 10, 8. Don't forget to use a 0 for a placeholder if you're missing one of the factors, or one of the degrees, rather. So I'm going to bring down a 1. 2 times 1 is 2. Combined with 1 makes 3. 2 times 3 makes 6. Combining 10 and 6 makes negative 4. 2 times negative 4 is negative 8. Combining with that gives me 0, which we expected because the problem said this is a factor. So if I didn't get 0, I would know I did something wrong. But now I'm going to take what's left over. We were cubic, so now we go quadratic, plus 3x minus 4. I'm going to take this. I'll rewrite it so that it's a little easier to see. X squared plus 3x minus 4. And I'm going to factor this. Well, minus 1, positive 4 gives me a negative 4, and it combines to 3. So I now have all the factors. I can now say that x cubed plus x squared minus 10x plus 8 equals this factor times this factor times this factor. Why is that helpful? Because now, if I set this original polynomial equal to 0, I can set this product of factors equal to 0 and solve each piece. X minus 2 equals 0, or x minus 1 equals 0, or x plus 4 equals 0. Graphically, this means that the graph of this polynomial right here crosses at 2, 1, and negative 4. X equals 2, x equals 1, x equals negative 4. When I put all 3 of these numbers in through synthetic division, I would get a remainder of 0 for all of them. Now, back when we learned synthetic division, we knew that we could not do problems when the leading coefficient of my divisor was not 1. Like right here, it equals 2. So we have to do something to compensate. So one option is to simply use long division, but another option is to divide everything by this coefficient. Now we're going to have some fractions to deal with, but that's okay. So now what I actually have is 3x cubed minus 12.5x squared, or 25 halves, plus x plus 4. And my divisor becomes x plus 1/2. So what goes in the box? Negative 1/2. And then I'm going to write my coefficients. 3, negative 12.5, 1, and 4. And we're going to first bring down the 3. 3 times negative 1/2 is negative 1.5. When I combine those, I get negative 14 times negative 1/2 is 7. 7 and 1 makes 8. 8 times negative 1/2 is negative 4, which gives me a remainder of 0, which we fully expected. So my new reduced or depressed polynomial is 3x squared minus 14x plus 8. And now we can continue to factor this polynomial. I have to think what multiplies to give me 3 times 8, or 24. -1 and -24, -2 and -12, -3 and -8, -4 and -6. And you can see right here, a few factors back, we have our winning combination. I'll put it underneath 3x, -2 and -12, and then I'll reduce 3x minus 2 and x minus 4 are our remaining factors, along with the original factor that we already divided by. Okay, the remainder theorem says that when you divide a polynomial by a factor, it is the constant f of a. The remainder will be. So if that factor happens to be a factor of the polynomial, you're going to get 0 for your remainder. But otherwise, you're going to get a number. For instance, right here, x plus 2 is not a factor of this original polynomial. And when I divide by it, I get 8. What this literally means is f of -2 equals 8. It is not a factor. We could also find f of -2 with a method called direct substitution. That's what we've done in previous steps, where we just simply take out the x and put in the -2 and compute. Either way, we get 8. So we're going to practice, instead of using direct substitution, we're going to practice using synthetic substitution to find these numbers. Now, the only difference is you don't put the opposite number into the box as we do when we start with a factor. When you start with a factor, you're going to take the opposite of what's next to the x. Here, there is nothing next to an x, it's just -5. So we're going to put -5 in the box. Then we're going to write our coefficients, and we're going to do synthetic substitution, or synthetic division, as we like to call it. That makes 15, which makes 20. This makes -100, -101. This means that f of -5 is -101. That was pretty fast. If I had to do it the other way, f of -5, I'll do it with direct substitution. -3 times -5 squared plus 5 times -5 minus 1. This gives me -75 minus 25 minus 1, which gives me -101. So you can see that it's another nice method for computing these numbers, especially when you have fractions. Let's try it with a fraction. Let's compute f of 1/2 over here. So I'm going to put 1/2 in the box. Then I'm going to write my coefficients. 1, 0, don't forget that placeholder, and the other placeholder for x, -1. Bring down 1/2. When I multiply, I get 1/2. Got carried away, got a step ahead of myself. Bring down the 1, actually. 1/2 times 1 makes 1/2. Combined with 0 is 1/2. 1/2 times 1/2 is 1/4. Combining with 11 is 11 1/4, which I could also call 45 over 4. When I multiply that by 1/2, I get 45 over 8. Combining with 0, 45 over 8. Multiplying that by 1/2, lots of fractions here, 45/16, minus 1, which is like subtracting 16/16. And when I do that, I get 29/16 for my answer. So that means f of 1/2 is 29/16, which I know it's a lot of fractions to deal with, but that's actually sometimes easier than trying to put a fraction in direct substitution.